Hi everyone, we are now already in a sixth session. We will discuss about transient response in this session. Okay, in the previous session we have already discussed about the different classes of second order system, and same like what we did in a first order system, we are going to discuss on how to estimate the parameters of this second order system based on the response of the system. But before that, in order to be able to estimate the parameter of the system, we need also to be able to quantitatively measure the performance of the responses in terms of the speed, in terms of the accuracy. So there are a few things that you can quantify. We will discuss it in the next few slides. Those are delay time, rise time, percent overshoot, and settling time. This is a typical unit step response of a second order system, but what you see here in this slide is in particular a unit step response of a second order system when we have an under damped case. So in particular, this topic we are only discuss on how to assess the performance and how to estimate the parameters of a second order system for under damped case. We are not going to talk about the other three cases. Let's start it with discussing on the performance of the second order system from a unit step response. If we have a unit step response or a step response of a second order system with an under damped case, typically there are a few measures of the characteristic of the responses that you can evaluate from the response itself. Those are, as I have already mentioned in the previous slides, those are delay time, rise time, peak time, maximum overshoot, and settling time. But what again, I need to underline it here again, what we are going to discuss in this topic is only for under damped second order system, which means when your zeta is between 0 and 1 only. Okay, let's take a look again the typical unit step response of an under damped second order system. If you have an under damped second order system, when you give a step input to the system, as you have already known, we have already discussed it in the previous topic, the response typically will oscillate. And if you have a stable system, the response after some time will converge to a final value, will converge to a steady state value. In this example, the steady state value will be equal to 1, around this value, right? At the beginning, it is oscillating, but the oscillation is damped here. If you look at this typical response, again, as I mentioned, there are few features that you can see. The first one that I want to discuss is the delay time, and normally is annotated as TD. So what is delay time? Delay time is the time that is required by the response to reach half of its steady state value. So in this example, the one that you see in this slide, the steady state value is 1. Half of 1 is 0.5, of course. So TD, or delay time, is the instant that is required by the response to reach the half of the steady state value, which is 0.5. So this is the delay time, right? So this is the first features that you can see from a step response of an under damped second order system. The second feature that you can see from unit step response of an underdamped second order system is rise time. By definition, rise time is the time required for an underdamped system to rise from 0 to 100% of the steady state value. So it's the time required by the system to reach the steady state value for the first time. There is a direct formula to estimate that if you know the parameters of the system. So if you still remember, you can refer back on our discussion about underdamped system for the first time. If we have underdamped system, the poles of our second order system will be complex conjugate as represented by this equation, right? And the poles are represented by the two parameters of the system, which are zeta and omega n. So if you look at this equation of the poles are determined only by zeta and omega n. And this rise time, you can estimate it if you know these two parameters, the zeta and omega n. The formula to estimate the rise time, you can see it in this slide. So if you look at the formula again, the rise time only depend on zeta, and in our formula here depends on the damped natural frequency omega d, but omega d basically is also determined by omega n and zeta. So in general, your rise time depends only on zeta and omega n. One thing that I want to discuss a bit further, you have seen this drawing before. So if you plot the poles of your underdamped second order system in the S-plane, if you have underdamped system, of course, you will have complex conjugate pair of poles, which is formulated as you can see in this slide, okay? Depends only on zeta and omega n. And if you draw these two poles on the S-plane, it will be, one will be here, the other one will be here, right? The real part here is represented by this length in S-plane, right? Because the horizontal axis represent the real part of your poles, and the vertical axis is the imaginary part. So basically then this length is your imaginary part, right? Looking at this pole location in the S-plane, then you can also immediately see that the length from the poles, either one of these poles, to the origin, okay, so this length is equal to the omega n, is equal to the undamped natural frequency, one of the parameters in your second order system. And another interesting thing is that this angle, the angle that is formed by the line from the poles to the origin and the horizontal line, which is beta, will tell you the zeta of your system, where zeta here is equal to cosine beta. You know about this. So how this will help us in estimating again the rise time? The equation of the rise time, as you can see here, because of the relationship of this omega n, zeta, omega d, and sigma, okay, you can also write it as follows. What does it mean then? Imagine if you have an underdamped second order system, but somehow you can keep the real part constant, okay, by any means. If you keep the real part constant, the zeta, omega n, or the sigma constant, the speed of the response of your underdamped second order system can be improved by increasing the imaginary part only. Why is it like that? Because as you can see in this equation, if you can increase the omega d, the imaginary part, your rise time will drop, which means the response of your system will become faster. Okay, so we have already discussed about the delay time, we discussed about the rise time. The third feature that I want to discuss with you in terms of the step response of an underdamped second order system is peak time, TP. So what is peak time? Peak time is the time required by the system, by the underdamped second order system, to reach the first peak on the response. So again, if you refer to the typical step response of an underdamped second order system, the response typically is like this. It is overshooting, and then the amplitude is getting smaller until after some time the response reaches the steady state value. So peak time is the time needed by the system to reach the first peak. So this is the peak time, the time required by the system to reach the first maximum. Again, peak time, you can also estimate it if you know the parameter of the system. Pretty similar to estimating the rise time, peak time depends only to zeta and omega n. So if you know zeta and omega n of your second order system, you can estimate your peak time easily. Just refer to this equation in this slide. One thing that you might want to note also that if you look at the response of this second order system, the step response of this underdamped second order system, basically it is an oscillation, right? An oscillation that the amplitude is damped, but from an oscillation you should be able to find the period. Period is the distance from one peak to another peak, or from one valley to another valley. So if you look at this, the distance from 0, which is the lowest point in your sine function here, in your oscillation here, to the first peak in here, basically this is half period of the oscillation, right? So your peak time basically is also a half period of the oscillation of your response. Okay, now the fourth features that you can see from a step response of an underdamped second order system is maximum overshoot. So what is a maximum overshoot? As you can see again in this drawing, this is a typical step response of an underdamped second order system. If you look at this, the response is overshooting, so it goes to a maximum value in here. What maximum overshoot says, maximum overshoot represent how high the response is overshooting maximum to the steady state value. So maximum overshoot, or we call it MP here, basically will tell us how much the response is overshooting to the steady state value in a percentage. So basically, maximum overshoot is the ratio between this distance and the value of the steady state. So this distance basically is the response when time is equal to TP, equal to the peak time, which is this value, minus the steady state value. So the steady state value, I can call it as the response when time is equal to infinity, and this basically is the response when time is equal to the peak time. So as you can see here, maximum overshoot is this distance again divided by the steady state value. If you know, again, same like before, if you know the parameter of your second order system, you should be able to estimate the maximum overshoot as well. How to do that? You can just refer to this formula. But different than the previous case, the case of the peak time, rise time, delay time, the interesting thing of this maximum overshoot is that maximum overshoot only depends to zeta, only depends to one parameter of your second order system, which is zeta. While in your peak time and rise time, both of them depends not only to zeta but also to the omega n. Okay, so this brings a nice consequence. If you know the maximum overshoot of the system, on the other hand, then you should be able to estimate the zeta of your system. If you know the maximum overshoot of the response of your underdamped second order system, you should be able to estimate the damping ratio zeta. So imagine if you have a second order system underdamped, but you don't know the parameters of the system, you don't know the zeta, and you want to find the zeta value of your second order system. So what you have to do, you just give a unit step input to the system, record the response. If after you record it, print it, take your ruler, measure the maximum overshoot. After you get the maximum overshoot, you can use this formula to estimate the zeta value of your system. Okay, the very last features that I want to share with you is settling time. So what is the definition of settling time? Again, let's refer again to the typical step response of an underdamped second order system like this. So what is settling time? Settling time is the first instant when your response reach and stay within a specific window, within a specified allowable tolerance. This window can be a 5% of the steady state value. It can be 2% of the steady state value, depending on what convention you want to use. So if you look at this illustration here, let's consider that this is the window that I'm referring to. So if you look at this, the response reach within the window and it stays within that window forever, but it reached for the first time at this point. So this is what we call as the settling time. Again, the window can be 2% or can be 5%. Of course, if you have bigger window, let's say, your settling time will be shorter, right? Like in this case, if you get bigger window, your settling time might be this one, right? So depending on the window that you are talking about here, if you are using 2% criterion of your window here, which means the window that you are using now is the within 2% of the steady state value, you can estimate the settling time again if you know the parameters of your second order system, because the settling time will be equal to 4 divided by zeta omega n. And for a 5% window, the settling time will be equal to 3 divided by zeta omega n. This settling time is similar to peak time and rise time. This settling time depends on zeta and omega n as well. So referring to all of the features that I mentioned, all of them depends on zeta and omega n except for maximum overshoot, MP. Maximum overshoot only depends on zeta. Okay, so from there you should be able to estimate the parameters of your second order system using the maximum overshoot feature. as we discussed before in the previous slide, we will be able to estimate zeta. So once you know zeta from the maximum overshoot, you can estimate the other parameters, which is omega n, using, let's say, settling time. You can use settling time, peak time, or rise time to estimate the second parameter, which is omega n. Okay, so that's basically how to estimate the parameters of your underdamped second order system. First, again, just to highlight again, first you use the maximum overshoot to estimate zeta, and then use either settling time, peak time, or rise time to find the omega n. A few remarks that I want to mention here. You still remember, I hope, when we were discussing first order system. In first order system, there are two parameters, the DC gain K and the time constant T, right? You can refer back to that tutorial if you need to refresh your memory again. So there are two parameters for a first order system, which are DC gain K and time constant T. In a second order system, there are three parameters, right? DC gain K, damping ratio zeta, and undamped natural frequency omega n, right? Just a side note for you, some textbook, they are talking about time constant of a second order system. What does it mean? If you are encountered with this terminology of time constant of a second order system, what they meant by time constant of a second order system basically is this value, the inverse of zeta omega n, 1 divided by zeta omega n. Okay, and as I have already discussed previously in the previous slide, normally when you want to estimate zeta from an underdamped second order system, what do? We just observe the maximum overshoot of the step response, and then from there, using the formula, you should be able to estimate the zeta, the damping ratio, right? Using this formula. Once you know the zeta, you can estimate the second parameter, omega n, using the other feature like settling time, peak time, or rise time. The easiest way is by using the settling time. So for instance, after you manage to measure the settling time from the step response, you can estimate the omega n, right? Because your settling time appears as a function of zeta and omega n. Zeta, you have already found it from the previous step. And then using the settling time, you can find the last parameter. So in short then, if you have the step response of an underdamped second order system, so let's say you have an underdamped second order system, you want to identify the parameters, just give us step input to it, record the response. So the response typically like this. From this response, you just take your ruler, measure the maximum overshoot, measure the rise time, peak time, settling time, whatsoever. And then once you know all of those parameters, using the formulas that you have seen before, you should be able to estimate the parameter of the system. On the other hand, if you know the parameter of the system, the zeta and the omega n, and also the DC gain, you should be able to estimate this feature. You should be able to estimate the rise time, peak time, settling time, and maximum overshoot. Once you know this feature, you should be able to sketch the response, right? Because the response, this step response, is fully characterized by these features, by the settling time, peak time, rise time, maximum overshoot. Okay, just a few side note again. Of course, maximum overshoot and peak time only apply to underdamped system. Why? because it's only underdamped system that will give an overshoot in your response. For the rest, if you are talking about overdamped, critically damped, or undamped, for undamped, the response is always oscillating, so you cannot identify the overshoot there. For overdamped or critically damped, there is no overshoot, there is no oscillation. So peak time and maximum overshoot, both of them do not apply to overdamped as well as undamped systems. Okay, when we are designing a system, let's say by a chance you are going to design a second order system, underdamped second order system. Normally, the rule of thumb, we always choose a damping ratio between 0.4 and 0.8. Why? If we have a too small damping ratio, if zeta is too small, smaller than 0.4, normally we will have a large overshoot. And overshoot is not a nice thing, of course, right? Imagine if you are sitting in the car, but the spring of your car, the shock absorber of your car has a very low damping ratio. If your car is passing through a hump, then your car will keep oscillating. You don't like it. On the other hand, you also don't like to have a damping ratio too large, because if the damping ratio is too large, the response will be too slow. Okay, and if you want to have a very fast transient response, you have to choose a large omega n, a large undamped natural frequency.